Depth-wise separable convolutions, or sometimes simply separable convolutions, are variations of the standard convolution. Now, the whole motivation for having a separable convolution is so that we can do something similar or same as convolution, but with lesser number of parameters. Now let's see how. Imagine you have an input image that looks like this and say it has 16 channels. Whatever dimensions we have, it doesn't matter for our discussion here. But let's say we have 16 channels. And then say I'm applying 32 3x3 filter. So I'm specifying 32 3x3 filter, but since the filters automatically adapt to the number of input channels, it automatically understands that the filter depth, each filter must be of depth 16. So I have 3x3 filter and the number of channels in the filter, or the depth of the filter, is 16. So when we convolve these 32 3x3 filters to my 16 channel input, what comes out is dimension. Say if this is x and y, same size input, maybe x minus 2 and y minus 2, but the depth of this will be 32 because we have 32 input filters that we are multiplying. So each filter gives me one channel, the second filter gives me second channel, and so on. So I get 32 channels in my output. Now we may see this as something that looks like this. So we have these 3x3 matrices, 16 of them in one single filter, right? So let's break it down so that we have 3x3 matrices, 16 of them sitting side by side or sitting separately. So this operation can be viewed as my first filter multiplies my first channel, second filter multiplies my second channel, third filter multiplies my third channel, and so on. So my first filter, 3x3 filter, so this is simply 3x3, depth 1, a basic 3x3 matrix, multiplies with my first channel, another 3x3 matrix, so this filter multiplies my second channel, this one multiplies my third, and the last filter multiplies my last channel. And then we simply sum them all together, right? So we multiply with the first one, and then we all sum to obtain the single channel output of one filter. So this is the standard convolution operation. So this is the standard convolution operation. Now the trick behind depth-wise separable is that what we want to do now is we don't add these. So we multiply the first channel with my first 3x3 value. We've also multiplied my second channel with my second 3x3 value, and so on. So instead of performing these additions that we have, we don't add, but we simply stack them so that this output comes in, this multiplication output comes in as my first channel, second channel, all the way in last channel. So I have 16 channels because my input is itself also a 16 channel. But now we have saved some computation by having to pixel-wise add all of these channels. Next, what we do is we simply, on these stacked channels, we simply apply a 1x1 convolution, 32 of them. So in this way, what I get is, since this is 1x1 convolution, I will get an output that's same size as input, maybe x and y, minus 2 and minus 2, because we already multiplied here 3x3, 3x3, so we'll get a small output. This is already x minus 2 and y minus 2. But the depth is 32 because we have applied 32 1x1 filters. Now 1x1 filters actually have way less parameters because here in the original convolution, the number of parameters we have is each filter needs a 3x3/16 number of parameters, ignoring the bias, and then we have 32 of them. So this is the total number of parameters that we would have if we used regular convolution. But in this case, you can see that we have 32 filters, but each of them only have 1x1 matrix weight. So this is actually 1x1/32 for all the 32 filters. So in this way, we get the same output as so this is my convolution output, and this is my depth-wise separable convolution output. So output 1, and I have output 2. We still get the same output, but with much lesser computation. So here, what we have done is here we have multiplied 3 by 3 with the first, 3 by 3 with the second. This gives me total, so we have 3 by 3 matrices doing 16 multiplications plus 32 of the 1 by 1 by 16 filter, because these 1 by 1 filters have to match with the input, so actually their depth should be equal to the number of channels in the input. So this number that we have, the total number of parameters that we have, is actually much less than the number of parameters that we have if we use regular convolution. So in this way, even though the end result is same output, depth-wise separable or simply separable convolutions save a lot of number of weights or number of parameters of neural network. Now, performance-wise, actually, it turns out separable convolutions have similar performance as regular convolutions, right? So it never hurts to use separable convolutions if you particularly want deeper neural network with a lot of parameters, such that your training becomes much faster. The overall goal when designing convolutional neural networks is to gradually increase the receptive field. Now, one way to do that is to increase the filter size, but then that really increases the number of parameters in the neuron, in the overall network. So increasing filter size is not a good idea. One tweak is to use something called dilated convolutions. So this is a variation of convolutional neural networks. In Keras, it's very easy to do this. You simply specify dilation rate. If you keep the dilation rate as 1 by 1, that means it's the standard convolution operation. But if we increase it to 2 by 2 or 4 by 4, then that really means that we are using dilation. Here's the idea behind dilated convolutions. Imagine that this is your input image, so image, and this is your filter, convolutional neuron, and here's your output, right? So usually, so far, what we have seen is the filter is a fixed 3 by 3 matrix that multiplies with the input. But here, you can see that there's a spacing between the items, elements in the filter, such that the input filter does not multiply the first, second, third, fourth, fifth, sixth, seventh, eighth item, but instead it skips one position and multiplies with items by skipping the position. So if we have a, say for example, an input image that looks like this, then a 3 by 3 filter usually multiplies like this with the 3 by 3 cell in the input image as well. But instead, if we use the same 9 values, 3 by 3 values, and multiply the input image by skipping one pixel at a time, so this is my first multiplication with my first value, we skip one position, second one, skip one, third one. This way, what I have is the filter now is able to, or my single convolutional neuron is able to see a bigger picture of the input. Similarly, I can increase this skipping equals 2 each time. So here I skipped 1 at a time, here I could skip 3 at a time, and then even have a wider vision. So wider vision of my input. So the overall idea is to increase the receptive field. So for increasing the receptive field, pooling and even started convolutions are common, but both reduce the resolution. That is, when we do max pooling, what happens is we are taking the maximum out of the 4 by default, skipping some of the important details that are out there, right? So pooling works, but dilation could work better. Dilated convolutions allow exponential expansion of the receptive feature field. So we can still decrease the input image size and increase the receptive field by controlling our dilation rate, and we can actually go beyond just 2 by 2 or whatever size we want, but maintaining the resolution, that is without the loss of resolution, and with same computation as convolutions, but by simply using this trick of skipping one pixel or a few pixels at a time. Now, practically, however, it is not equally exciting for all problems. For certain problems, dilated convolutions work way better, and for certain problems, they're not as great as you would expect them to be.